share my screen with you guys. So we are still discussing chapter number 7, Root-Locus method. We discussed last week what does Root-Locus mean. It is basically the collection of all the roots of the denominator of your transfer function, what we call characteristic equation, if the controller gain is changing. So with each change of the controller gain, you can plot the roots of the quadratic equation, the roots of the characteristic equation on the S-plane. And when we collect all those roots, they make different sections. And the collection of those sections is called Root-Locus. And the number of sections depends upon the power of the polynomial of the characteristic equation. If it's the power 4, then of course, anytime you change the value of the controller gain k, you're going to get 4 roots for each value of k. So you plot those 4 roots on the complex plane. And remember, I did not give you the project. I was contemplating if I should ask you to do that, something like this, like I did myself. And I think I gave it last time I taught it. But I think Root-Locus function that is in Octave or MATLAB RLocus X and in MATLAB RLocus, they're pretty good functions, and they give you all the information about all the values of k and stuff. But just make sure if you are plotting this, just understand what exactly you're plotting. You're plotting each root on the S-plane. So if this is the S-plane, you take the real part of S, real part of the root, and plot it versus the complex part of the root. So as you can see, when I put a cross over here, grab my pen. When I put a cross over here, let's say, then I'm basically plotting my real part, which is whatever the value is this, -5 point something, versus the imaginary part. So whatever root you're getting, let's say s is equal to 5 plus minus 5j, j5, basically both of these roots are plotted on the S-plane for a specific value of k for which the equation yielded these roots. And you separate the real part and the imaginary part, and then you plot real versus imaginary on the S-plane. So understand when we say plotting the poles or plotting the zeros, that's what we mean. It's very easy to do it. If the roots are in front of you with your hand, you can always put a cross or a circle for 0 and a cross for pole. But when you're doing it through programming, you have to separate the real part and the imaginary part, and then plot the real versus imaginary on the S-plane. So as I said, I didn't really give you the project, and I'm not planning to give you this project. It's just gonna you'll have to spend a lot of time of doing this when we already have good functions available in Root-Locus, in RLocus X and stuff. So I think I'll give you one more project from chapter number 8 though, which is the frequency response of the control systems. So there would be just 2 projects basically throughout the semester. Okay, so we covered all this thing. There were issues here because of the simplification process, but you understood the idea what we were trying to do. And the topic for today, and that's the only topic for today, and that's what I said, we should be able to finish pretty early. So the topic for today is a very important controller type, which are called PID controllers. And they are used very frequently in control system theory, as well as in practical application wherever you are creating a control system or a system for a specific purpose. And what that purpose is, we're going to look at in this section. So what PID means? PID means that these controllers are proportional to the input, integral to the input, and derivative of the input of this section. So remember, you have input coming in, what we call RT usually, and then you have the sum And then you have the controller usually, GC, and then you have the process, G, and of course your output, Y. So this is RS, and then you have YS, and then feedback loop. And most of the time we have unity feedback loop. So this controller is where you implement the PID controller, basically, as you know, you can say the name controllers. So that's PID. In many of the processes, this controller is what is replaced by PID controller. So the input of this controller, of course, is the error E, and of course, output is the signal that is controlling the process. So as I said, PID stands for proportional, integral, and derivative. Proportional to the value of E, integral to the value of E, and derivative of the value of the error signal. So it basically processes the error signal in 3 different ways. And then all of those are added together. And the resultant signal goes into the process to control the process, change the values of the process based on how far you are from your desired result. And remember, the desired result is usually that your output should be close to the input, because this is our desired output, R is our desired output, and Y is our actual output. So the error signal, of course, is the difference between the actual the desired output and the actual output. All right, let's look at in the time domain first. So in the time domain, PID controller, this is the input of the PID controller, E, as I mentioned, and we assume that U is the output of PID controller. So the output of the PID controller is equal to Kp times Et. Kp is the proportional, so it's a gain basically. So error signal is multiplied by a gain value. Then that is added into the integral of the gain value times the gain, the integral of the error value times the gain of the integral, Ki, and then the derivative of the error value times the gain of the derivative, Kt. So if we look at the controller transfer function, the transfer function of the controller is Kp, which is the proportional gain, plus Ki over S. Remember, integral, and let me open chapter number 2, where we have the table. Let's open that. Let's see right here. So if you look at the Laplace table that we discussed, integral, someone has a question or something? Right. So integral of f is fs over s plus 1 over s, the initial value. And derivative of f, the kth derivative of f, s to the power k fs minus sk minus 1 f0 negative and stuff. So if you take the first derivative of f, df over dt, then it's s to the power 1 fs. So derivative in Laplace domain is s times fs, or s times the function, Laplace function of whichever input you have, and the integral is the function, the Laplace of that function that you're using, or Laplace of that input that you're using, divided by s. So our controller gain is Kp plus Ki over s, since we are taking the integral, plus Kt times s. Again, this is the derivative. And this is the block diagram of the PID controller that I mentioned. So this is your GCS right here. This is your GCS.
Do the letters PID stand for something specific?
Yeah, proportional, integral, derivative. The proportional, of course, as I mentioned, the error signal is multiplied by the gain. So it's going to be proportionally. So it's going to the error signal is going to be, or the output, sorry, the output will be proportional to the error signal. And integral, of course, that you're taking the output is integral of the input signal, which is the error, and of course derivative is the output is derivative of the input signal, which is the error. So U is the output of the controller, and E is the input of the controller, which is the error signal. This is your GCS, and this is your GS, which is the process. So PID controller, why they are superior than the regular controllers? Because the performance of simple feedback controller determining how much and how fast corrective action can be applied to a process by changing either the integral of that or derivative of that or the proportional amount of that. So it can change 3 quantities at the same time to bring the output such that when that output is fed to the process, the error signal can be minimized between the input and the output. So how each of them work, let's look at that. So for proportional block, the output signal is proportional to the magnitude of the error signal, as I mentioned. And proportional block is also called, or also it can be related as the information that is the present information, that information, and use that information to produce the output signal. So this is your input signal, error signal right here. And that is multiplied by a constant value, Kp, and the output signal is produced. So gain times error, that's your proportional block. For the proportional gain, the closer we get to the desired output. So this is your desired output right here. And this is your actual output. Input value, also called the desired output, which is basically your input value, R. It's also called the set point, which you can see over here. SP, it's hard to see over here, but this is SP, which is set point, which is also the same as the input value. So the closer we get to the desired output, the less it will push the actual output. Eventually, the process just runs smoothly close to the set point, but not quite there. So it's going to be close to the set point, but there will be always a small bit of error between the desired input and the actual output. And that, of course, is the steady state error, as you can see. So our goal is to push that steady state error further down, of course, such that it will match the desired input or match the set point when it is going to go to the steady state. But if you have simple proportional block, then it's going to run it close to it, but it may not always become equal to the value of the set point. The second block, integral block, it uses the past information. So proportional block uses the present information. Integral block creates an output proportional to the duration and magnitude of the error signal. So whatever the duration of the error signal, whatever happened in the past, it uses that information and the magnitude of that, and then produce the output of that corresponding to the error signal. So it uses past information instead of present to generate a signal to control the process. The bigger the error, the longer the error, and the greater the amount, the larger the integral output, as you can see over here. So this is your input error signal, assume. You have a blue line and kind of dark blue line, 2 lines. So if the input signal is smaller with a dark blue line for a smaller amount of time, then your, of course, it's a constant value. So when you do a constant integral of constant, it's going to be a ramp signal. So it's going to be a ramp signal until the output is constant, and when until the input is constant, and when the input goes down to 0, then the value of the integral is just gonna become constant value, which will be the initial based on the initial condition. If the error signal is larger for longer amount of time, then of course the slope of this line is going to be higher, and the constant value is going to be higher as well. So integral basically is doing the integral gain and integrating the error signal from 0 to t, whatever the time it is lasting for, starting from the very first value to whatever the value of t is. So as long as the error exists, integral action will continue. When the error is eliminated, the integral term will cease to grow. Of course, as we can see, it becomes constant when there is no error, like you do in the integration. And when the error is eliminated, the integral term close to 0. P and I together will push the actual output closer to the set point. So as you can see, without integral, you had some offset between the desired output and the actual output. And if you include the integral as well, then it's going to try to push it closer to the set point or closer to the actual value. And the third block is the derivative block that creates an output signal proportional to the rate of change of error signal. Of course, as we know what the derivative do. It generates the rate of change for any variable that you're taking the derivative of. The faster the error changes, the larger the derivative output, as you can see in this. So this is your error signal. And it's calculating the slope of the error signal. This is increasing time derivative action. So the error signal slope is larger or smaller based on that. Either it is changing faster or slower. That's going to create a constant value at the output of the derivative. But that value is going to be larger if the slope of the error signal or if the rate of change of error signal is faster. And it's going to be a smaller value if the rate of change is not that fast. So we have the present input, which is the proportional. We have the past or the past action, which is through integral. And derivative produce a future trend of the error signal based on the current rate of change. Many times derivative is not really important, as you saw here, that even with proportional and integral together, you have, it's going to push it down to the set point. But many times it is important. Many times it is important to know how fast the error is changing so that you can control the parameter that you're changing. You can control that so you don't overshoot, basically. Yeah, you don't go beyond, in second order system, we discussed the overshoot and all those things. So if you don't consider properly how fast or how slow your error is changing, then it's possible then that you overshoot, and then you'll have to, you're going to come down, and then you'll have oscillations and stuff before you settle down. So we also don't want to overshoot the output. We don't want to oscillate too much. And that oscillation is generally controlled by the derivative block to see that we should change the output of your PID controller such that based upon how fast or how slow the error is changing. And there's a video that we're going to watch, and that video actually made this concept very clear. Many times derivative block is not used because it's very sensitive to the measurement noise. Why it is very sensitive to the measurement noise? Remember, derivative of a function, dx over dt, if x value is changing, even if it's very small, but it's changing for a very short amount of time, the derivative of that is going to be quite large. A very small signal that exists for a very short amount of time. the derivative of that signal is going to be quite large because the rate of change is going to be very large for that signal. So sometimes measurement noise, they last for a very small time, or measurement noise is small, but they also last for very small time. So when you measure the magnitude of, so because remember derivative measure slope, so when you measure the magnitude of the measurement noise and the amount of time that they last, whether it is microsecond or millisecond, then the ratio of the magnitude over the time is usually quite large. And that's why sometimes derivative control can produce large changes in very short amount of time and can kind of throw off the system as well. So although they are used, but it's possible that in PID controller, D is not present, only P and I is present. That's also possible. Generally in the motion control application, D is present. So most of the PID controller work fine with proportional and integral gains and do not use derivative gain. However, again, as I said, it depends on the application that you're using. Derivative may or may not be present. So I'm gonna go ahead and we're gonna watch this video. So if you have any question about PID, then you can answer this. Let me know if you can hear the voice.
PID control.
Can you hear the voice?
Chances are you've interacted that uses a form of this control law, even if you weren't aware of it. And so it's worth learning a bit more about what this control law is actually doing and how it helps us. However, often when we're learning something new in control theory, it's easy to get bogged down in the detailed mathematics of the problem. So in this video, we're going to skip most of the math and instead focus on building a good intuitive foundation. So I hope you stick around for it. I'm Brian, and welcome to a MATLAB Tech Talk. We start with a plant. This is what we call the system that we want to control, or the system whose behavior we want to affect. The input into the plant is the actuating signal, and the output is the controlled variable. Different industries refer to these signals by various names, so you might hear them called something else, like plant input and plant output. But regardless of the names, the basic idea of a control system is to figure out how to generate the appropriate actuating signal, the input, so that our system will produce the desired controlled variable, the output. And that's basically the job of the control engineer: produce the right input into the system to get the output that you want. And just like before, the output you want also goes by various names. Here I call it the command, or the commanded variable, but you might also hear it as the set point, the reference, or the desired value. And in feedback control, the output of the system is fed back, hence the name, and compared to the command to see how far off the system is from where we want it to be. This difference between the two is the error term. If the output was exactly what we commanded it to be, then the error would go to 0. And that is what we want, 0 error. So the question is, how do we take this error term and convert it into suitable actuator commands so that over time, the error is driven to 0? And the answer is with a controller. Let's illustrate this with an example. Imagine you are standing on the goal line of a soccer field and you want to walk to the half field line 50 meters away. In this case, you are the plant. The actuating signal is the speed and the direction that you walk, and your current location on the field is the output variable, or 0 meters to start, and then 50 meters is the command. Therefore, at the beginning, your position error is 50 meters, or 50 minus 0. You still have a ways to go. Your brain, being the controller, tells your legs how fast to walk. And one way your brain can do this is to use the error at the present moment to decide your walking speed. Here, I've set our controller to the value of 0.1. This means that if we take the error in our system and multiply it by 0.1, we'll get our walking speed. So if our error is 50 meters like it is at the beginning, then we'll start off walking at 5 meters per second. With a proportional controller like this, we start reducing the error quickly since we're far away, and then gradually slow down as we get closer and closer to our goal. In this way, we would eventually and asymptotically reach the half field line, at which time the error would be 0, and our proportional controller would multiply that by 0.1, which would generate a walking speed of 0, stopping us right where we want to be. If we wanted to adjust the amount of time it took us to get to the goal, we could increase or decrease the multiplier term. Regardless of the gain value chosen, this type of controller will eventually cause us to stop right on the goal line. So this proportional controller seems great. I mean, just multiplying the present error by a number seems to work. Well, let's try it again on a different system and see if it performs the same way. In this second example, you want to design an altitude controller for a quadcopter drone. The drone has 4 propellers, and when they all spin up together, they produce a force that lifts the drone up into the air. This is similar to our walking example in that we're trying to get to a specific location, but this time we want to get our system to hover at an altitude of 50 meters. Our plant is the drone, and the output of this system is altitude. Now, the input of the system is not walking speed, but propeller speed. And all in all, it seems like a pretty similar problem. So how well does a proportional controller work in this case? Well, when the drone is on the ground, there's an error of 50 meters, which would generate a large propeller speed, causing the drone to lift off and start to rise, reducing the error. So far, so good. But let's imagine the drone was able to rise all the way to 50 meters. What would happen now? Well, the error would drop to 0 since the command and the output are both 50 meters. This would then shut off the propellers, lift would stop, and the drone would fall back to Earth. Now, when that happens, the propeller speed would start to increase again as the error grew. There is a certain propeller speed where the lifting force is exactly equal to the weight of the drone, and at that speed, the drone will hover. So where would our proportional controller hover this drone? Well, that depends on the controller gain. Now let's assume for the moment that the propellers need to spin at 100 RPM in order for the drone to hover. If our proportional gain was 2, then the drone would hover right at ground level, since an error of 50 times 2 is 100 RPM. However, if we increased the gain to 5, the drone would rise at first, but then stop at 30 meters, since the error at that point would be 20 meters, and 20 times 5 is 100 RPM. A gain of 10 would produce an error of 10 meters, and a gain of 100 would produce an error of 1 meter. And no matter how high we increase the gain, the error won't go away. It'll just get smaller and smaller with this system and a proportional controller. So we can see that a simple proportional controller doesn't work in every situation. It works with our walking example, but for our drone, it created this constant error. This error is also called steady state error. So how can we tweak our controller to get rid of this steady state error? We can do that by letting our controller use past information, or specifically adding an integrator path in our controller that's added alongside the proportional path. An integrator sums up the input signal over time, keeping a running total. Therefore, it has this memory of what has happened before. Basically, it's keeping track of the past. Now, if the drone gets to steady state below the desired altitude, the error term is non-zero. And when a non-zero value is integrated, the output will increase. Now, as long as there's error in our system, the integral output will continue to change. And this increased value from the integrator path will increase the speed of the propellers, and the drone will continue to rise. These two paths, the proportional and the integral path, work with each other to drive the error down to 0. And with this controller, when the drone is hovering at the desired altitude of 50 meters, the proportional path is doing nothing since the error is 0. But the integral path has been summing and subtracting values until it came to rest at 100 RPM. Remember, this is what we said was needed for the drone to hover. And that output from our integrator will not change since the input to the integrator at this point is 0. All right, this proportional integral controller is it. This is what we want, right? Something that understands the present and has memory of the past. Well, looking at the past and present error will get us to our goal in this situation. However, the path the drone takes to get there might not be ideal. Imagine this situation. Right before we get to 50 meters, there's an interesting situation that can occur. The proportional path is basically 0 since at this point the error is so small. But depending on how the drone got to this height, the integrator may have summed to a value over 100 RPM. This would cause the drone to keep rising, which is what we want since we're below the 50 meters. However, to remove that excess propeller speed, the drone will have to go higher than our goal to create a negative error. This negative error, when summed, lowers the output of the integrator and slows the propellers down. This overshooting of the goal might not be desired. Luckily, there is a simple way around this problem, and that is by adding a path to our controller that can predict the future and respond to how fast we're closing in on our goal. And we do that with a derivative. A derivative produces a measure of the rate of change of the error. That is, how fast the error is growing or shrinking. For example, if our drone is rising quickly and fast approaching our goal, this means that the error is quickly decreasing. That decreasing error has a negative rate of change, which will produce a negative value through our derivative path. That negative value will be added to our controller's output, therefore lowering the propeller speed. Basically, our controller is using changing error to determine that we are closing in on our goal way too fast, and then prematurely slowing down the propeller speed, preventing the drone from overshooting. And just like that, we've created a PID controller, proportional integral derivative. This is a versatile controller that uses the present error, the past error, and a prediction of the future error to calculate the appropriate actuator commands. These three branches each contribute some amount to the overall output of the controller, and as the designer, you get to decide how to weigh each contribution. You do this by adjusting the gain term in each branch. This is called tuning the controller. Now, if your controller contains all three branches, it's called a PID controller. Now, if the gain of one or more branch is set to 0, taking it out of the equation, then we typically refer to that controller with the letters of the remaining paths. For example, a PI or a P controller. PID is just one form of a feedback controller, but they're pretty easy to understand and implement. They are the simplest controller you can have that uses the past, present, and future error, and it's these primary features that are needed to satisfy most control problems. Not all, but a lot of them. That's why PID is the most prevalent form of feedback control for a wide range of real physical applications. Now, there's a lot more to learn on this topic, and if you stick with this series, we're going to explore
So as you saw, the importance of reducing the error using the present information, past information, and of course the future information when you're designing a control system. That's a very good series. You can check out more videos from this series. I put the link over here because when I make the PDF file, I don't think it's going to embed the actual video in the file. So I have also put the link over there as well. So you can, if you want, you can also watch the other videos in the same series. Any question about what do PID controllers do?
No questions.
I have a stupid question on the drone thing that I kept thinking about. So is this having an altimeter just giving it constant input at the same time?
So, right. So you are measuring the speed with which it is going towards a specific height because you want to run the propellers with a specific speed until it will hit that height, and you don't want to overshoot. So there is a feedback coming, whether that feedback, of course, since it's a drone, so it's coming through some sort of wireless, whether it's the speed, basically you're measuring through some sort of wireless link. And with the speed, you can always calculate at what height you are there, or if you know the height, then you can calculate the speed by looking at how long did it take for the controller to get over there. So you need basically, from the basic physics, we know that S is equal to S is equal to VT, where this S is the speed distance what was that? Forgot my basic physics. You have rate of change of distance is a speed. So velocity is equal to rate of change of distance. Del D. There was some equation in the physics S is equal to VT or something like that. Anyways, so the velocity with which it is moving up and the distance that it is covered, or the time that it is taking to get to that value, you can easily calculate at what distance the drone is going to be hovering. So you need basically two things in this equation. You need the velocity, or you need the distance that it has covered for a specific amount of time to calculate the velocity, or to calculate the distance, you need the velocity and how long did it take to go to a specific height, basically. So yeah, feedback in this case, well, in that video specifically, you saw that the feedback was the height that it wants to reach, and based on that height, when you multiply that by the gain, then that gain is going to produce the specific speed that it should run at to get to that specific height that you want to hover it on. So the feedback in that specific video was the altitude, was the height at which it is hovering. So yeah, it is, whether it's what you call the altitude meter or anything, but the feedback is coming through that meter that is measuring the height from the ground level. So as you saw in the video, if we set the gain of one of the branches to be 0, then you can get PI controller or PD controller. That is, one of them is just going to be 0, and the transfer function of the controller block will be dependent upon 2 gains instead of 3 gains. We can also look at the PID controller as a cascade of PI. So this is proportional and integral, and this is proportional and derivative. PI and PD controller. Oh, let's look at this. So PI controller gain, we can write down as KP plus KIS. Just, we want to make them a little bit different, so we are putting the tilde on top of those to represent that these gains are from the PI controller. And then PD controller, we have KP and KD. So these gains are from the PD controller. If you put them back to back in cascade, so this is PI and this is PD, then you can also get the controller gain for the PID controller. As you can see, when we are in cascade, of course, we can multiply the transfer functions of each one of them. So we multiplied the transfer functions, collected the like term, the constant term, the term with S, which represent the derivative, and 1 over S, which represent the integral. So in this case, as you can see, this is the constant value, which is the gain of KP. This is the S term, that will be KD, and then of course KI is going to be this term. So 2 controllers connected in cascade, 1 PI and 1 PD, can also produce a PID controller. An example. So KP over KIS plus KDS, S is the common factor in the denominator. So we can also write the gain as KDS square plus KPS plus KI over S. If we take if we divide both sides by KD for this, or if we take the KD value as a common factor, so that our S square term has 1 coefficient, then we can write down S square plus AS. A is going to be KP over KD, which is right here, plus B, and B is KI over KD. So we are basically taking KD S square plus Kp over Kd, S plus Ki over Kd over S. And this is our A, and this is our B. So we can write down this second order equation as S square plus AS plus B. Kd is our gain of the total, the controller gain. And S square plus AS plus B can be broken down into two zeros because again it is in the numerator, so that's zeros. S plus Z1 and S plus Z2, they can be real values or they can be complex conjugate values. And we have one pole at S is equal to 0, as you can see. So let's look at an example for a unity feedback control system. Let the process transfer function given by GS. So this process transfer function is 1 over S plus 2 and S plus 3. So we have two poles at S is equal to -2 and S is equal to -3 for the process. Let's use a PID controller with complex roots, -3 plus minus ji. Therefore, the transfer function of the system will be given by. So this is our PID controller right here. And we are assuming that we have two zeros, one at -3 minus ji and one at -3 plus ji. So we're going to put -3 minus ji for Z1, -3 plus ji for Z2. And of course, Kd is the derivative gain. So Kd times S plus minus 3ji. So this is our PDI controller. This is our GS. And B, calculate the transfer function of that. GCS GS over 1 plus GCS GS for the feedback loop. And after we simplify this, we're going to get 1 plus Kd, S square plus 6S plus 10 over S cube plus 5S square plus 6S. After the simplification of this equation. So this equation is basically your characteristic equation of the denominator. So this is just a simplification of the denominator right here. And when we do the root locus of this for different values of Kd, you're going to get you're going to get 3 sections because you have cubic equation in the denominator. You're going to get 3 sections. You have 2 zeros, of course, at -3 plus J1 and -3 minus J1. You have poles. As you can see, we have 3 real poles of this equation, S cube plus 5S square plus 6S. So one pole is going to be at S is equal to 0. One pole is going to be at -3 and one pole is going to be at -2. -2 times -3 is 6. And then you're going to have 5. So 0, -2, and -3. 3 poles and 2 zeros. And 1 zero is going to be at infinity because we have 3 sections, 2 zeros which are not sitting at infinity, and 3 poles. So one of the zeros is going to be infinity, which will be right over here somewhere when you hit infinity over here. So the root locus from this pole, which is at S is equal to -3, is going to head towards the 0, which is sitting at negative real axis. And from these poles, as you can see with different colors, so they start moving towards each other when you change the value of Kd. Then the locus of roots are going to start moving towards each other. And at the breakaway point, whichever the breakaway point is this, they're going to break away from the real axis, and the set of poles that is coming from S is equal to 0 is going to go to this 0, and the set of poles which is coming from S is equal to -2 is going to move towards this 0, which is over here. So why we are doing this? again, we are changing different values of KD, which is the derivative gain. And we are trying to see what value of KD is going to produce our desired roots for the desired output. And what is the desired output? It's going to come in a little bit. As the same as the picture from the book, and this is exactly the Root-Locus that I created with my program. This is the same thing from the book. So any complex conjugate zeros, we can write the transfer function of the system as KD S plus Z1, S plus Z1. And then S plus R2, S plus R1, S plus R1. These are the roots, one real root and two complex conjugate root. The same Root-Locus is shown for generic values of zeros in figure 7.110. Any zeros, basically negative Z1 and negative Z1 complex conjugate. Observe that the two complex poles are moving towards complex zeros, and the third pole, which is real, is moving towards the third zero located at infinity, as I discussed with you on the previous slide. So let's see the response, how the response is going to look like, the output of the system is going to look like. When KD value is maximum, so I gave the maximum value of 10 in my program. Of course, if you use R-locus X, you can find the other maximum value because mine is still going towards 0. So when K was 10, then basically you have the roots right over here. This is for K is equal to 10. I can increase that value and it's going to move further towards the 0. So for the value 10, complex poles are closer to complex 0. Their values are negative 3.1099 plus minus J1.3. And the value of real pole is 8.7. It should be negative. Yeah, negative is here, so it's negative 8 point. So it's negative 8 point something that is shown over there. Substituting these values in 7.24, the transfer function can be written as. So I went ahead and I substituted these values for the poles. 8.7803, 3.10 for the value of KD, that is 10. So this is KD. And then whatever the transfer function came out to be, I created the step response of that, a step function. And from the step response, I observed that my peak value is 1.0447. My steady state value, remember, is 1. This is for the unit step, basically. Peak time is 0.47 seconds. Overshoot is only 4.47%, and settling time is about 1 second. So again, goal is what? Goal is to make this go to the steady state value, because that's our desired output, without overshooting much, like we saw in the drone example, that we don't want the drone to go up and then come down and then go up and come down until it will hover at that 50-meter mark. We want it to start slowing down as it is moving towards that 50-meter mark. And that was done through the derivative loop, as you saw. So in this case, when the derivative gain was chosen, the last value that is chosen, which is close to the 0, then you saw that the response of the curve is pretty nice response. If it becomes even closer to the 0, then the overshoot is even going to be smaller than 4.47%. Now, since you have the value of KD, and you can, again, do that from R-locus X, any value of KD can be calculated. You can go back, actually, and you can calculate the values of KP and KI, or sorry, KP and KI, because we know the value of A and we know the value of B from the quadratic equation that we have. Whatever the quadratic equation we created, S plus 3 minus JI, S plus 3 plus JI. So quadratic equation, whatever you have the value of A, you have the value of B from there. And using that, and since we already know KD, you can calculate the value of Kp and Ki. So all three gains can be calculated from the value of Kt, since you already know value of A and value of B in the quadratic equation. And a couple of more slides to just discuss. System exhibit desirable characteristics with less overshoot, small settling time. If even a smaller settling time is required, system design should include the two complex zeros to be further left in the complex plane. And the value of Kt should drive roots near complex zeros. Table 7.1 shows the effect of increasing different PID gains values on the step response. As you can see, if you increase the value of the proportional gain, percent overshoot is going to increase. It's not going to be much impact on the settling time. Steady state error is going to decrease. If you increase the value of the integral gain, percent overshoot will increase, settling time is going to increase, and it's going to drive it closer to the steady state error, zero steady state error. And if you increase KD, then percent overshoot will decrease, settling time will decrease, but the steady state error will not have any impact. So basically KD or the derivative is controlling how fast or how slow it should go towards the target, so it won't, go above the target, as we saw in the video. But it's not going to affect anything as far as steady state error is concerned. The first two conditions, P and I, controls the steady state error. Together, they can create a zero steady state error. But the value of overshoot and transitions, that is how fast should go to the settling time, that is controlled by, or that can be controlled by changing the value of the derivative gain and adding it to adding it as a third block in addition to the proportional gain and the integral gain. So once again, very common controller that is used even in the digital, when you're using the digital control system. I think somebody in the senior design project is using it, PID controller, to, I think, I don't know who is using it. Someone was talking to me, and they are using it on Raspberry Pi when they are controlling the motion of something or something like that. So I forgot who is using it. But yeah, it is used very commonly, basically. The idea is pretty straightforward as how you're going to control the error using the three blocks. And how do you change the value of the three gains? There are two commonly used ways, manual tuning and Ziegler-Nicholas tuning. Manual tuning is basically you plot, like I'm plotting it here, you plot the response, and then from the response, a manual tuning value of gains are determined using simulations for a step input with minimal analytic analysis. So you plot the response, and then from that response, you calculate the value of KD, and from those, you can calculate the value of KI and KP as we discussed. In some cases, actual testing on the system is done, and gains are decided based on experimentation and observation. And Ziegler-Nicholas is more analytic. And again, I'm not going into that. It can become a little complex. But yeah, that's more analytic as how you're going to change the three values using mathematical relationships and all those things. So I get only one example over here, and that's good enough for this course. Again, I don't want to make it too complicated. But this is an example as how you can choose the value of KT for, or choose or look at the value of KT from the Root-Locus. And based on that value of KT, you can calculate the step response. Again, everything can be done in Octave or MATLAB. And then you can see how long is the settling time, what is the overshoot and stuff. And based on those characteristics, you can choose another route, check the value of KD for that, and see how your response is gonna look like. So if you want, as we discussed, if these zeros can move towards left a little bit, then as we were discussing over here, system exhibit, if shorter settling time is required, system design should include the 2 complex 0 to be further left in the complex plane, and value of KD should be close to those complex zeros. So that's going to reduce the amount of settling time. For us, of course, settling time was about 1 second that we discussed. It can be further reduced. The steady state can be achieved earlier. But if settling time is reduced, sometime your overshoot can be a little more. It can go up and then come down quickly. So there are compromises that you will have to do. But again, for the manual tuning, of course, you go with the Root-Locus, use the values from the Root-Locus for the value of KD, calculate the KI and KP, plot the response first, and then choose a desired value of KD that can give you the desired output response. And then you can calculate the value of KI and KP for your control system from that value, as I explained.